All right, we'll go ahead and get going. We're going to finish up on radicals today. That means we're kind of done with chapter 15 today. We'll also start in on chapters 13 and 14 today. So yeah, I don't think the chapter 15 study guide's due for a couple more days, and that's fine, but we'll be moving on from that later on today. I just wanted to spend a little bit more time talking about polymers that come from radical polymerization, because a lot of the materials that you encounter in your everyday life, from the carpet you walk on and the shoes that walk on the carpet, to the chair you're sitting on, to the bottles of soda and various things, all of them are related to polymers. And so it may be the part of chemistry that you have the most experience with. I think we talked last time a little bit about polyvinyl chloride. These polymers are named according to the individual monomer starting materials that are used. In this case, this molecule is vinyl chloride because the chloride is attached to the vinyl carbon. Remember, vinyl carbon is the word we use for a carbon that's participating in a carbon-carbon double bond. And the polymerization process happens with a radical initiator. We generally aren't going to care what that is, though folks in industry that make these things will. The radical attacks the pi bond to create a new sigma bond between the initiator and the less substituted carbon of your olefin. And what that does is that puts a radical on the more substituted carbon. You don't have to scramble to copy all of this down. The notes will be available. I drew it out ahead of time just to facilitate the discussion, because the chemistry and the mechanism, at least, isn't new, but I want to spend some time talking about the properties of these polymers. So again, you attack and create a new bond with the less substituted carbon, so that the more substituted carbon can have the radical. I haven't shown it, but you could draw a resonance structure in which there would be a pi bond between these two carbons and an unpaired electron on chlorine. And that resonance stabilization is why this process is regioselective for having the radical on the carbon that is also bonded to chlorine. Once you've got that new radical, it can encounter another monomer of the vinyl chloride to create another bond and a new radical, and so on until you start to extend the polymer chain indefinitely. And you do this until you run out of vinyl chloride monomer. And so the number of individual polymer subunits can be in the hundreds to thousands. Go ahead. I just said you could draw a resonance structure like this, where instead of the radical being on the carbon, you create a pi bond here, and then there's an unpaired electron there. That's stabilizing, and so that's why it's better, and the bonding selectively favors having the radical adjacent to the chlorine. It's kind of like the Markovnikov rule for adding to olefins back in chapter 10. Okay. You can control the length of the polymer chain by controlling the amount of radical initiator you have relative to starting material. So you might imagine if you add a ton of radical initiator, you're going to have lots of polymer chains growing at the same time. You're going to run out of vinyl chloride monomer sooner, and so your chains are going to be shorter. Instead, if you add less radical initiator relative to your vinyl chloride, you'll start fewer chains. They'll run out of monomer slower, so they'll each get to much longer length. And so there are different processes, different setups for generating polymers of different length. How does the polymerization process stop? Well, it only stops rarely, and that's why the polymers are so long, but it happens through any sort of chain termination event. So you could imagine two elongating polymers with radicals on either end, and you could imagine them forming a new sigma bond that would terminate the radical reaction on either side. So that's one of the things that can happen. I'll show you another in just a second. The polymer is called polyvinyl chloride, or PVC. Recycle number 3 on various products. If you see that, used a lot for pipes and fittings and hoses, flooring, decking, vinyl decking. In the vinyl deck materials in the pandemic were very hard to come by because everybody was at home and thinking, well, I haven't got anything else to do, maybe I'll build a deck. Let's see, there's potential in all of these radical polymerization processes for branching. So if you look at that polyvinyl chloride chain, there's still a lot of carbon-hydrogen bonds that you could imagine doing radical chemistry with. There are 2 different kinds of carbons in the polymer. You've got the carbon attached to the chloride and then the CH2 group that's in between places where the chloride is. A radical will selectively remove a hydrogen from a carbon adjacent to a chlorine to generate the more stable radical versus the other possibility where the radical would be there. And this happens in an uncontrolled way with some frequency. There are methods you can use to suppress branching, but if a radical forms here, that then becomes a new starting point for another polymer chain that can grow out in this direction. So here we have this radical adjacent to the chlorine attacking the pi bond of another vinyl chloride monomer, and that's going to create a new bond here with a new radical there, and then we can continue adding vinyl chloride subunits in an alternative direction. So now we have a polymer growing in this dimension and in an orthogonal dimension. And the more branching the polymer has, well, that can affect its properties, and we'll talk about that in just a second. But questions at this point? Yeah?
Where would be the main source of vinyl chloride that is used in like PVC piping and decking?
Where do you get vinyl chloride from? Let's ask the Google, for whom we are very grateful. You can get it from a number of different routes. That's not that helpful. You can make it from acetylene, actually. So maybe that's a maybe chapter 10 or 11 chemistry. You can take acetylene, which you can get from petroleum. You can add HCl to get vinyl chloride. So I'm not sure what the most abundant way of doing it, but yeah, ultimately from petroleum products. Other questions? Okay, so any molecule with an olefin in it, anything like this 2-carbon olefin, and anything you can think of attaching there, you could make a new polymer. So ethylene itself is the simplest of these polymers. We didn't start with it because it's easier to tell what the polymer is when you've got this group branching off the main chain at regular intervals. But you can start with the olefin that doesn't even have anything other than hydrogen at this position, and you can create what's called polyethylene. Here are the individual ethylene subunits highlighted in pink. Here are branching points. The branching process happens for ethylene just like I showed it happening for polyvinyl chloride. If there's a lot of branching, it's called LDPE, which stands for low density polyethylene. This is highly branched. It has the recycle code 4. It's often used in food containers, bottles, tubing. It's very flexible. In contrast, if you don't do a lot of branching, you've got what's called high-density polyethylene, or HDPE, recycle code 2. This is much more rigid and is used in toys and signs, containers that need to be stronger. The reason the high-density polyethylene is stronger than the low-density is because the extended chain allows individual polyethylene chains to pack against each other more tightly. It's exactly the same principle we discussed last week about why saturated fats are solid at room temperature, whereas unsaturated fats are not, right? The more you have an extended hydrocarbon chain that can tightly pack against other hydrocarbon chains, the higher the higher the melting point is going to be, the stronger the interactions are going to be. Branching gets in the way of that tight van der Waals packing, and so LDPE is far more flexible than high density polyethylene. And you'll find both of these in various applications. Polystyrene is another. Instead of having a chloro at this position, we have a benzene ring, and that changes the property. You know, PVC is quite rigid. Polystyrene can be rigid, but it can be machined in other interesting ways. For example, the polystyrene polymer can foam up as you're making it. If you blow air through it, you can create a sort of more fluffy polymer for packing peanuts or food shell containers. Depending on how you manipulate that polymer, you can make forks, knives, spoons, and sporks. Another interesting property of polystyrene is you can change its shape with temperature. So, and I'm not just talking about, throwing plastic forks in the fire on a camp out. You've probably done that before and seen the fork start to melt and distort itself. That's just you breaking up van der Waals interactions and that hold the individual polymer chains in shape. But you can process polystyrene in a way that sort of pulls the chains and stretches them out as much as possible. And you can get this kind of polystyrene in thin, transparent sheets, which you can buy on the internet and then take home to your kids, and then you can draw interesting things on them, cut out the shapes that you've drawn, put them in the oven, and you heat up the polymer, and it snaps back from being extended and condenses to a much smaller shape, and you now have a shrinky-dink. Some of you may have played with this before in your past. It's kind of a thing of the 80s, so maybe not. But next time you go get takeout from somewhere and you've got this clear plastic container, if it says it's polystyrene, just cut out a square, draw something on it, cut out the thing you drew, stick it in the oven, and watch it shrink. It's really kind of fun. We did this last summer in the early days of the pandemic when we were all bored out of our minds and the children needed something to do besides sitting on their beds looking at screens, and so we did shrinky dinks. There was a Baby Yoda shrinky dink, there was a Mandalorian shrinky dink, there was a Mandalorian Death Watch symbol, Mythosaur symbol shrinky dink. Once you make them, you sort of just stare at them and then throw them in a drawer and forget about them, but it was kind of entertaining, and it's fun to watch. The process of shrinking happens over the course of a few minutes. This weird spork drawing is from last time. That's because of there was some concern among folks. I wasn't sure whether people of your generation knew what the spork is, because we don't generally do sporks much anymore. Mostly because if you're going to use it as a spoon, why do you want to risk being stabbed? But there's a VeggieTales video called Lord of the Beans, which is a parody of Lord of the Rings. I can't remember what the moral lesson is, but the bad guys were the sporks, kind of like orcs. Anyway.
Oh, I never got that.
Yeah, get it now? That's a pretty long wait for it, for the punchline, but now you got it.
About 10 years?
Cool. Changing the groups, polypropylene just has a methyl group instead of a benzene ring as in polystyrene. Polypropylene is resistant to mechanical stress, so it's used a lot for various containers. The next polymer, vinyl acetate. Again, you can see the 2 carbon subunits here, except the highlighting is not going well. And you've probably eaten this polymer before. It's what makes Elmer's glue work. When Elmer's glue dries, its exposure to oxygen causes this polymerization process to happen. And therefore, those of us that have eaten Elmer's glue and are still here, this polymer is considered relatively safe. It's used as envelope adhesive. You guys don't know what envelopes are anymore, but you lick the envelope to seal it, and you were licking vinyl acetate in that case. It's also a major... let's see, Teflon is just like ethylene, only each of the CH bonds is replaced with a carbon-fluorine bond. And that changes the properties dramatically. Carbon-fluorine bond is polar, but fluorine, being very electronegative, isn't that inclined to hydrogen bond with water. It doesn't really, sharing doesn't really do much for fluorine. But it's also not that inclined because the electrons in fluorine are held very tightly, so it's hard to get an induced dipole. And this is why polytetrafluoroethylene places. It's also used as plastic in some on your pots and pans in Teflon. If you have little black card and or you need a new pan. Career in dentistry someday should be aware of this beautiful monomer. Now it looks insane, but actually it's just like the propylene monomer, only you've attached something else at this carbon that links two individual monomers together. This is called BGMA, and it's a major component of dental composite. So if you've had a filling before, you go to the dentist or something, and then they start drilling. And if you're lucky, you get that soul-shattering sound, and it rattles in your ears and your brain. And if you're really lucky, you'll smell some tooth smoke. And after they've drilled out the cavity, then they pack it with dental composite. Among the other things that are in it, you've got this polymer. And then you may have noticed the dentist will take out this little gun that has a bright blue light. The dentist will put some lenses on you to protect your reflected UV light from going back on the dentist. And she'll stick it in your mouth and then press go and hold it there for a couple of seconds, and then you're done. That process, the reason you needed the UV light was to initiate radical polymerization. It had vinyl chloride. The difference is that you've got this green linker. It's not actually green, but this linker cross-links two of the chains, and it has to be cross-linked here, and the other will be cross-linked to a third, and so on. So you get this really large matrix of polymers. All right, so painting, cooking, dentistry, pipe, all of that is something you may have some experience with. I started up the sprinklers this weekend and there weren't any busted pipes, so yay, that was horrendous. What is the process for recycling some of these polymers? Well, for some of them, you would just need to heat them up past their melting point and peanut butter or snot stuff, melt it and reuse it. There are some polymers that are more difficult to recycle than others. I've heard occasionally you'll hear some sort of depressing statistics about how much of what we put in the recycling bin. Usually it's just a function of the ability of the local recycling plant to handle different types of plastic. Sometimes they can't recycle what, unfortunately. We could ask the Google, but yeah, go ahead.
How do they change the product between 4 and 2 there, shown at the top? Like
how do they control branching? Yeah, so they use actually a non-radical process for the linear one. I forget what it's called. I want to say Ziegler-Netta catalysis or something like that. But they use a method for that one that happen as easily. All right, what else? In high school, they made shrinky-dink periodic tables. Whoa, that just blew my mind. presumably for cheating on the test. That's not exactly what was said, but no, I'm just kidding. You'll notice Kirsten, I'm sorry, I was not accusing you of cheating. I was just attempting to make a joke, and it was bad. That's this portion of the molecule. These oxygens directly attached to the benzene ring are called phenolic oxygens. The bisphenol A molecule looks like this. It's got a quaternary, and this happens to be a really useful and I think cheap to make starting polymer chains together. So it's not only used in the Bis GMA dental composite, but it's also used in a lot of epoxy glues and resins. We haven't talked about epoxide polymer, a lot of different plastics. Now, you maybe have seen, if you've been shopping for baby bottles or like to buy canned foods at the supermarket, you may have seen the label BPA free. What it means is the plastic that you just bought doesn't have now, why wouldn't you want BPA in your baby bottle or in the epoxy lining of your cans? I actually didn't know this, but the cans that you buy, canned goods, epoxy polymer. And it used to be that coating had a lot of bisphenol A in it. It turns out that bisphenol A has been shown to bind estrogen receptors, though with 1,000 to 2,000 times lower affinity than estradiol. And look at estradiol. It also has a phenol OH group. And then there's another OH group on the other side, and the distance is, not that far off from this. And so you can imagine how a receptor for estradiol might also bind. The actual effects of this, it's controversial, though it's risky enough in terms of development that the FDA now bans BPA for use in baby bottles. There continues to be debate as to the effects and risk to the general population. Cautionary principle. This is the idea that if there's even a remote chance that a chemical might have harmful effects, we should treat it with maximum caution and not use it. The challenge with that is just that probably consider the potential rewards for use of a chemical versus just the risks and try to be reasonable about it. And so, that being said, industry will give consumers what they want, and consumers want the piece to stop being used quite as much. Anything else you've heard about that you want to talk about? Okay, lastly on radicals, I wanted to just mention antioxidants because they came up in a couple of questions. Are molecules that can react with radicals to generate a more stable radical that's not inclined to react very much at all. So shown here is resveratrol. This is present in grapes and in red wine. Some so-called French effect of being able to have a diet rich in saturated fat and red meat and nonetheless not get heart disease, to the action of resveratrol, though that conclusion is controversial. The way these work as antioxidants is they intercept more neutralize them or inactivate them. So imagine hydroxy radical, which is pretty reactive. It can remove very easily a hydrogen atom from resveratrol. The resulting radical is stable because of resonance. You can draw resonance structures in which that unpaired electron is on these atoms all the way across the ring. And that delocalized radical is much less reactive and doesn't go on to do damage. There are others that you may have heard of. Periodically, you'll find a kiosk in a mall that's telling you about the massive antioxidant properties of green tea extract. One of the molecules that's responsible for that is epicatechin. The structure is complicated, but just look at all the phenolic OH groups. Each of those is a radical trap, and that's how it works. Now, the NIH website, National Institutes of Health, says that the clinical trials in terms of the benefits of taking antioxidant supplements versus just eating a diet rich in various foods plus antioxidants. The conclusion, it's inconclusive, and it doesn't look like there's a huge benefit for consuming lots of antioxidant supplements. There are different reasons why that might be the case, but it probably is not worth it to spend large amounts of money and or subscribe to services that send you lots of antioxidant supplements. Okay. Anything else on radicals you want to talk about? All right, so we're going to talk next and for the rest of the semester about how we know what we know. And that could be an interesting lesson spiritually, but what I mean is how do we know what we know in chemistry? When we say we've done a reaction, how do we know we got this product and not that product? And so there are a few things we need to confirm that we've got the right product in organic chemistry. We need to confirm that the product has the right molecular formula. And one of the ways we do that is we measure the molecular weight. And we don't do that using a scale. We use a technique called mass spectrometry. And that is discussed in some detail in Chapter 13. We're not going to delve into the specifics of how this technique works. If you want to take an analytical chemistry class and learn about that, you certainly can. Mass spectrometry works on the principle that charged particles move in a magnetic field in a way that depends on both their mass and their charge. And so if you take a small molecule and figure out a way to give it either a positive or a negative charge, and then you put it in a magnetic field, it's going to move in a characteristic way that you can use to calculate the mass of that particle. On a mass spectrum, you typically on the y-axis have some units that describe number of observations. In a mass spectrometer, there is a detector that gets a little signal every time an ion hits it. And on the x-axis, you have the ratio between the mass of an ion versus its charge. And of course, if charge equals 1, then this is just simply molecular weight. And for everything you'll be doing with mass spec data, generally, they'll tell you what the M/Z ratio is for the singly charged ion. So you'll see a peak here at a particular M/Z ratio. Let's suppose that we were taking the mass spectrum of methane, CH4. What mass would we expect? Well, 12 and arithmetic, really. What, 16? No? Help me. 16, right? M/Z ratio of 16. And then we would know, okay, that's consistent with methane. There's more to talk about, but I think this will be enough for what we're doing. You're going to be looking for agreement between the predicted molecular weight that you're expecting versus what you observe. There's one additional detail that can be useful, and that is that in mass spec, you're seeing individual particles, not averages. I don't know if you remember learning in general chemistry how the reason we say that the molecular weight of carbon is 12.011 is because most of the carbon in the world is carbon 12, but some is 13 and some is 14. And this number is a weighted average of all of those. In mass spec, you're going to see what are called monoisotopic peaks. That is, you're going to see a peak at 16 where all of the carbons are carbon 12 and all of the hydrogens are just regular hydrogen. And then you'll see a smaller peak 1 mass unit away And that's where one of the carbons is carbon-13 or one of the hydrogens is deuterium and so on. And of course, the likelihood of seeing larger peaks decreases. But your text glosses over that, and so we will as well, except in the case of molecules containing chlorine and molecules containing bromine. So chlorine comes in two isotopic flavors, chlorine 35 and chlorine 37. Both are stable. 75% of the chlorine in our world is chlorine 35. The other 25% is chlorine 37. So if you have a molecule that has chlorine in it, suppose it were, let's try to make this easy on my brain, CH3Cl. Already 15 plus 35, 50, yes? So you would see a peak at 50, and then you'd see another peak at 52. And their relative intensities would be sort of 3 to 1. Because 75% of the molecules of CH3Cl will have chlorine 35, and the other 25% will have chlorine 37. And so if you see a characteristic pattern of peaks in a 3 to 1 ratio, 2 mass units apart, that's a dead giveaway for a molecule that has 1 chlorine in it. Same can be said for bromine. Bromine has 2 stable isotopes, 79 and 81, and it's about 50-50 for bromine. So again, if instead this was CH3Br, oh, horrible, 79 plus 15, carry the 1, 94. Terrible at arithmetic. You would see 2 peaks present in a 1-to-1 ratio, 2 mass units apart. And again, that's a dead giveaway for something that has bromine in it. So take a look at that and make sure you're able to reason through that. As I said, mostly we're going to be using mass spec data to confirm that we have the right molecular formula. The other thing we need to establish when we're trying to identify a compound is that we have the right functional groups. So as an example, with the same molecular weight, yeah. Okay. Is the y-axis number of times observed, number of observations? Yeah, sorry about that. Number of times a particular molecule was observed by the detector. So these two molecules have the same molecular formula, same molecular weight, but they differ in functional groups, right? One of them has a carbon-oxygen double bond, the other has a ring and an OH group. And there is a fairly inexpensive technique that can be used to distinguish between these two options, and this is infrared spectroscopy, or IR. Again, there's some physics here that we won't get into. IR is based on the idea that bonds vibrate. Okay, you can think of carbon, 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 hydrogen, all these bonds as being springs. And there are various allowed, what are called vibrational modes present in molecules. For example, for a carbonyl, there would be a stretching mode where the carbon-oxygen pi bond stretches in this direction at the same time as the adjacent carbon-carbon bonds are stretching in that direction. And that bond vibration has a characteristic frequency, and you can excite it with a characteristic photon, with a photon that has the right wavelength or the right frequency. Because bond vibrations are quantized, just like going from HOMO to LUMO is quantized. There's a specific energy gap. And it just so happens that the photon that can cause transitions in vibrations is in the IR region of the spectrum. Okay, so what does an infrared spectrum look like? Well, there's a lot of ways you could have designed it yourself, but there is the way that is mostly used. And scientists are creatures of habit, and so some of what I say here you may think is going to be not that as efficient as you might have set it up in the beginning, and all I can say is our predecessors did this to us, and so we just have to stick with it. In an IR spectrum, in an IR experiment, you're shooting infrared light of various wavelengths through a sample, and you're watching which wavelengths get absorbed and which don't. On the y-axis, we have something that's called percent transmittance, where it's 100 up here and 0 down here. 0 means everything was absorbed, no light gets through. 100% transmittance means all light gets through. So we're going to be seeing negative peaks. That is, if we see absorbance at a particular wavelength, we're going to see that at that wavelength, 0% of the light gets through, or 70% of the light gets through, or so on. Now, here's the stretch, and get ready. On the x-axis, you might think that we would use wavelength of light, which is usually in units of meters or centimeters or nanometers or millimeters or so on. Or alternatively, we could use frequency, which is in inverse seconds or hertz, number of waves per second. But that's not what the folks who invented IR chose to do. So energy of a photon is equal to Planck's constant times its frequency, right? And the speed of light is also equal to wavelength times frequency. That's physics. So we could combine those two and say that energy is related to Planck's constant times the speed of light divided by wavelength. So because this energy term, because the energy of a photon is related to the inverse of the wavelength, we're going to define a new thing to put on the x-axis, which is called wave number. Wave number equals 1 over the wavelength, and it's going to have units of inverse centimeters for whatever reason, okay? But what that means is lower numbers on the x-axis equal lower energy photons, and therefore lower energy vibrations. Higher numbers on the x-axis are going to equal higher energy photons, and therefore higher energy vibrations. So what you're going to see on the x-axis is this thing, wave number, in inverse centimeters. But just realize that's a way of describing, that's a number that's directly related to energy. The larger the number, the higher energy the photon. All right? It's weird, but that's what we're dealing with. The spectrum you will typically see will be from around 800 inverse centimeters to about 4,000 inverse centimeters. And the region that's sort of between 800 and 1,200 is going to be a fingerprint region that is fairly dependent on the structure of the molecule and difficult to interpret. So we will generally ignore that area of the spectrum. Up here, though, between 1,200 and around 4,000 wave number, you've got sort of the functional group region of the spectrum. Characteristic functional groups vibrate at certain frequencies. So for example, if you had a molecule with a carbon-oxygen pi bond, there's going to be a narrow and sharp and fairly deep peak at around 1600 to 1800 wave number in that region. That's where carbonyl vibration happens. Instead, if you had an OH group, there would be a broader and also intense but broader peak in the 3000 to 3500 wave number area. And other kinds of bonds will show up in different areas. These two are some of the most useful. If we did an IR experiment and we saw just this peak but not this one, we'd think, okay, maybe, and we already knew the molecular weight, we maybe would think this is a better option. If we saw just the peak for the OH group and not for the carbonyl group, we might think that this was a decent option. So you're going to use IR for functional group identification. All right. Yeah.
Is there a way to tell the difference between like rings and chains?
Is there a difference in IR to tell? Can you tell the difference between rings and chains? Not that I know of. That doesn't mean there isn't. It just means I don't know it. Okay. Others? So what we've got so far is certainly good for distinguishing between, say, a 6-carbon chain with an OH group and this 6-carbon chain with a ketone. Those would have different masses. And it's certainly good enough for distinguishing between these two possibilities where the functional groups are different. But what about connectivity? What about constitutional isomers? In other words, how would I tell the difference between this molecule and its constitutional isomer where the ketone is somewhere else? And if I look at that, I could say, well, the number and quantity of different kinds of hydrogens could be informative. In the molecule on the left, I have a methyl group here, but it's different from the methyl group there. So we might call these protons A, B, C, and D. The CH2 group B is different from the CH2 group C because these are closer to the ketone. So I would expect to see 1, 2, 3, 4 different kinds of hydrogens in that molecule, and there would be 3 of A and 3 of D and 2 of B and 2 of C. In contrast, for the other molecule, what would I see? Well, it turns out that this molecule is symmetrical, so these two methyl groups are the same, and these two CH2 groups are the same. So I would have only 2 different kinds of hydrogens, and there would be 6 of one and 4 of the other. So if I could get some information in terms of the number of different kinds of hydrogens and how many of each were present, I might be able to start to distinguish between these two options. And that's where the technique of nuclear magnetic resonance comes in. NMR is what we will call it. This involves using a strong magnetic field to sense hydrogen atoms. The technology involved in NMR is the same that is used in the radiology technique, magnetic resonance imaging, or MRI. Only the protons that you're detecting in MRI are from water. All right, so NMR is based heavily in nuclear physics, which I don't understand and apparently don't care to understand. But the great thing is you don't have to understand the physics to use the data. And in that way, it's really powerful. It can be used to great effect even by non-experts. But a little bit of understanding into the physics is helpful before we get into the details. So let's consider a hydrogen nucleus or a proton. It turns out that protons and neutrons, like electrons, have angular momentum or spin. And different nuclei have different spin characteristics. It's complicated, but for right now, it'll be sufficient to say that the proton has two possible spin quantum numbers. Its spin can be plus 1/2 or minus 1/2. All right? Kind of like the electron. However, sorry, there was no however there. So a proton has a spin or angular momentum. Now, charges, the proton itself is a point, it's not actually spinning. But in physics, you learn that charges that are spinning have a magnetic field. And in the same way, nuclei that have non-zero spin have a net magnetic moment. They can respond to magnetic fields. So you can think of the proton as a little magnet. Okay. So if the proton is not, if a sample that has lots of protons in it, we're not even worried about what they're bonded to. If there's no external magnetic field, there's no difference in energy to have spin 1/2 or spin minus 1/2, right? It doesn't matter which way a magnet is oriented if there's not a magnetic field for them to interact with. So we would say if this is energy at when there's no magnetic field, the spin state of being aligned with the field versus being aligned against the field, they're degenerate. They have the same energy. There's no energy difference. And so the population of spin 1/2 versus spin versus minus should be around 50-50. But if you put these protons in the presence of an external magnetic field, then you create an energy difference for being aligned with or against the external magnetic field. And that's all we have time for today, and we'll explain next time how that helps us know about the connectivity of a molecule.